that? Oh, it's just airplay. Okay. Okay, so second order rate law. This is the differential rate law. Again, these all start out as what is the rate, and from the perspective of a reactant. So it's the change in the concentration over the change in time. It's negative here because we're talking about a reactant. And when we set that equal to our sort of generic equation, which has this value of K in it, when it's second order, that's just the concentration of A squared. Taking the integral of that with respect to time, so from the concentration at 0 to the concentration at time t, we can reorganize this and we end up getting what is essentially an equation for a straight line. But it's only the equation for a straight line if I have 1 over the concentration of A at time t, and then equals kT plus 1 over concentration of A at time 0. So the concentration of A at time 0, that's our B for y equals mx plus b. And again, the slope tells us what K is. So if we look at some data, not the easiest thing to graph by hand, but also not that hard. But if you had something like Excel, you could type all these numbers in, although now even computers are good enough, you could probably just screenshot it and copy and paste the numbers into Excel, and then plot it. If you plot all of this as just time versus concentration, you would not get a straight line. And if you plot it as, if you remember for the first order rate law, that ended up being the natural log of the concentration of A at time 0, or at time t, equals negative kT plus the natural log of the concentration. So if we plotted the natural log and we don't see our data, so the data is, right, all these black dots, don't line up with this line, they're not a straight line, that tells us that this is not a first order reaction. The rate is not first order. If we plot it versus 1 over the concentrations, we get a perfectly straight line. Or with real data, you'd get really close to a perfectly straight line. So without, actually, it's like looking at this data, before if we wanted to tell what the order of a reaction was, we had data that said, okay, if I use this concentration of A, then I get this rate. If I use this concentration of A, then I get this rate. And we could do the rate 2 over rate 1, essentially, equation, and figure out what the order was. Remember that rate 2 over rate 1 equals K times 2 over K times A1. Actually put that outside, to the n. But we need rates. We need initial rates to use this equation. The data that we're given here does not give us initial rates. It doesn't even give us different concentrations. The method with these two equations requires that we have different initial concentrations and different initial rates. So we can't use this equation to determine the order from this data. Instead, one of the things we might do is, again, graph it. If it was 0 order, then we would just have a perfectly straight line, horizontal line. Rate doesn't change. First order, we get a straight line if it's the natural log. Second order is a straight line if we use 1 over the concentration, the inverse. Once we figured out that it's second order, then we could use the equation of the line or do a linear regression, figure out what the slope of that line is, and use that, because it's the integrated rate law, we could use it to predict what the concentration is going to be in the future. So, first order rate law, 1 over A at t, k, t plus 1 over A0 plus. So we want to find 1 over A at t. What's k? It's the slope, 0.255. And we get that just from the slope of the graph, right? And we can plug in time here, which was 2,000 seconds, plus we need the initial concentration. 100 molar. But what are the units for the graph? Or I guess, what does the y-axis represent on the graph? 1 over the concentration. So in our equation here, right, this is 1 over the concentration. So I don't do 1 over 100. This number here is already 1 over 100, so I just plug in 100. Because we're getting that data from the graph, and it's already 1 over the concentration. This is like 0.01. But and then algebra. .255 times 2,000 plus 100. .610, and then 1 divided by that. Or you do everything to the first power. Or to the -1, I mean. Three sig figs. Okay. Yeah, so as long as you know the equation for second order rate, because you might get a question where it doesn't have the previous slide and it just gives you this graph and it says, figure out what the concentration is at 2,000 seconds. How could you know from the graph that it's second order? We've got a straight line and the y-axis is 1 over concentration. If the y-axis was natural log of the concentration, that'd be first order. If it was, well, if it was just concentration, no, yeah, if it's just concentration, then it would just be 0 order. But then the rate doesn't depend on the concentration. Yeah. Yeah, so we had none of the 0. So 0 order integrated rate law, I mean, when we look at the equation for the rate, then the rate equals k. So rate equals k because a to the 0 is just 1, so that doesn't matter. Becomes 1, so rate equals k. So if we integrate this, then our 0 order integrated rate law is just the concentration of A at time t equals negative kt plus A0. So then the plot of the concentration versus time is linear. We don't have to do a transformation to the concentration to get a straight line. Oh, actually, here, let's just real quick summarize these. So the 0 order is just concentration. first order. And in my mind, it's kind of like as you go zero order, first order, second order, it gets more and more complex. So now we have the natural log with negative kt plus the natural log of A0. And for second order, not negative, plus. And of course, equations would exist for other orders as well, but we're not going to do those ones. Honestly, this is one of those things that's probably just best memorized. Make a flashcard, make 3 flashcards, and then for every single one of them, it's probably more important to be able to write out the equation rather than see the equation and write if it's zero order, first order, or second order. But if you see zero order, being able to write out that equation. And we can also write out when they're linear. So this one is just concentration of A versus time. For first order, it's the natural log of the concentration versus time. And for second order, 1 over the concentration versus time. Yep. So now we're going to look at another interesting property of these rate laws, which is half-life. And for half-life, we kind of have to change our perspective a little bit, because for these equations and these previous problems, we are trying to find the concentration of A at some time in the future. When we talk about half-lives, we're talking about how long does it take to get to 1/2. And how does that change for zero order, first order, and second order? And there's one simple trick that you can use to sort of easily figure out these equations if you know the integrated rate law equations. So half-life is always the amount of time it takes to get to half of, not even just the initial value, but the previous value. So if I start with 100, then the time it takes me to get to 50, or the time it takes me to get to 25 after that. So concentration to fall to 1/2. So for example, if we had an initial concentration of 0.5 molar, and we know the half-life is 50 seconds, what's the concentration after 50 seconds? 0.25. So after 50 seconds, now what's the concentration after 100 seconds?
0.125.
Yeah, 0.125. Because it's always half of the previous value. So we've gone through another half-life, but now we don't have 0.5. We're starting from 0.25. So it's half of that again. And then the next one would be whatever half of 0.125 is, and then half of that, and then half of that. But the half-life expression is going to be different for different reaction orders. So this one would be a first order. So first order reaction, the integrated rate law is as shown here, which is just a slight rearrangement of the natural log of concentration at time t equals negative kt plus natural log of A0. So if we subtract the natural log over there, then the natural log of something minus the natural log of something else is the same as the natural log divided by the natural log of the other. or I guess divided inside of the natural log. So if we want to solve for half-life, how long is it going to take to get to 1/2, then all we really need to know is a little bit of algebra, and that AT, right, the concentration at that time in the future, after 1/2 life in this case, is going to be 1/2 of A0. And for this one, the easiest way to plug that in, it's like mathematical semantics, because it all means the same thing. The easiest way to do that is we replace AT with 1/2 A0. But the way that you write 1/2 A0 can make this a little bit easier or a little bit harder. If we write it as 0.5 times A0, and then I just have A0 on the bottom. Equals negative KT. So what happens to A0? Cancels out. So for a first order reaction, the natural log of 0.5 equals negative KT, or again, a little bit of algebra, this becomes the natural log, and I think it becomes natural log of 2 over K equals T 1/2. The difference between the natural log of 1/2 and the natural log of 2 is one is negative and the other is positive. So what this tells us is the initial concentration doesn't matter for half-life if it's a first order reaction. The amount of time it takes to go from one half-life to another half-life is always the same. Like here, in this example, we've got a half-life of 100 seconds. And every time 100 seconds, or whenever 100 seconds passes, I end up with half of what I had before that 100 seconds. And the amount of time doesn't change. And this is a thing that is unique to first order reactions. It is independent of the concentration. It also makes first order half-life problems the easiest to do because we don't have to calculate how much that half-life is going to change. Wish they'd pick different colors for these. Oh, that's what I wanted. Oh, that makes it look black. Look at this. So there's 6, 7, well, that's 9. So 10 dots there. So when do I get to half? Five. So half-life is 90 seconds. All right, so I got another first order reaction. Half-life of 25 minutes. If the initial concentration is 0.3 molar, what is the concentration after 5 minutes? It's the concentration of B even. Right, so at time 0, nothing's been converted. at 25 minutes, how much has been converted? Half, yeah. 0.150. So this is going to be 0.150. What about at 50 minutes? So not half of the initial value, but half of the previous value. So this one will decrease by, or decrease down to 2.075. This will be B. So when you're working with like an exact number of half-lives especially, that's when you don't really need a calculator. You just say, how many times do I have to cut this in half? How many half-lives have passed? How many times do I cut it in half? But this is not, it's not like, 25 minutes passes and then magically half of it is Thanos snapped out of existence or converted over into the other. I mean, that's kind of what this is showing, that over time, a few of them are being converted. So there is this continuous conversion between half-lives. And that's why we have a half-life equation, is so that we can calculate at any time, not just exact half-lives, what the concentration is going to be. But for a lot of them, you can just hit divide by 2 and then answer divide by 2. So here's a good one. Alex likes these ones. I'll probably assign some of them because it is a different way of thinking. So first order reaction has a half-life of 26.4 seconds. How long does the how long does it take for the concentration of the reactant to fall to 1/8 of its initial value? So if we start at, well, all of it, and let's just say all of it is 1. We're going to do 1.00, and that's at 0 seconds. And we say, okay, 26.4 seconds. How much is left? 1/2. And then after another 26.4 seconds, 0.25, or you could say, 1, this is a half, this is a fourth. And so after 1 more, that'll be an 1/8. So another 26.4, so we end up getting 26.4 times 3. Yeah, that sounds right. The answer there. The other way you could do this is if we actually took the first order rate law equation and we said, I'm just going to use A. Well, if you think about it as, it would be 1/8 A at time t divided by A at t. Oh, I had to actually solve for. How did I do this on Friday? Oh, no, we know the half-life, right? Except I'm solving for t.
You can plug in t, since we know the half-life, and solve for the k. And then we can later plug in the j and solve for t.
Yes, that's what it was. Because we know that the half-life equation is natural log of 2 over k equals t 1/2. So we have to solve for k, and then you could plug in, oops, wrong spot. Plug in k and say a over 1/2, which ends up being the natural log of a over 8, sorry, 8 negative, and then whatever we found for k, and then solve for t. But again, if you're working with Like going to an eighth is easy because it's 1/2, 1/4, 1/8. You keep going, be a 16th and a 32nd, and just keep dividing by 2. All right, and then for the second order, this is our integrated rate law. But again, if we want to find out what the half-life is or how the half-life is related to the concentration, we're just plugging in 1/2 A0 for AT. So this is 1 over 0.5 A0 KT plus 1 over A0. Oh, and then this is the same as no, it's not. This is the same as 2 over. So if that's a half, then this is 2 over A0 equals KT plus 1 over A0. So now I can subtract A0 from both sides and get 1 over A0. Equals KT. So 1 over K times A0 equals T 1/2. Yep. So for a second order reaction, the rate depends on the concentration. Or the half-life depends on the concentration. So for a zero-order reaction, the half-life was always the same, always takes the same amount of time. What happens as my concentration decreases for a second-order reaction? Does the half-life get longer or shorter? It's longer. Conceptually, to answer this question, all you got to think about is if I plug in smaller and smaller numbers for A0, how does that affect the half-life? So if I'm dividing by smaller and smaller numbers, that means that the half-life is going to get longer and longer. So the half-life gets longer for second-order reactions as the concentration decreases. Which kind of makes sense because in second-order reactions, it means that there's multiple things that depend on, there's more things that are dependent, that the reaction is dependent on. And so as you run out of concentration, you run out of those really molecules to react. For zero order, again, we're just plugging in 1/2 A0 for AT. I'm going to do it this way because we can get rid of the negative. So KT now on that side, and this is 1/2 A0. So A0 over 2K. So now how does decreasing concentration affect the half-life? So here the half-life will get shorter and shorter and shorter. Because as A0 goes down, these are going to be constants. So yeah, divided by 2, also divided by 2k. But if this goes from 10 to 9 to 8 to 7, it doesn't matter that I'm dividing those by 2k, that half-life will get shorter for every interval. So half-life gets shorter as the initial concentration decreases, which also means that the reaction goes faster. All right, now here's the chart that has all of that. Zero order, first order, and second order. The rate laws, integrated rate laws, how you make those plots a straight line, and the half-life equations. All right, so I got a decomposition reaction with a rate that is observed to slow down as the reaction proceeds. Has a half-life that depends on the initial concentration of the reactant. Which statement is most likely true? I guess from this, can we say what order the reaction is? Rate slows down. Yeah. So from the fact that the rate slows down and the half-life depends on the initial concentration. Because the half-life depends on the initial concentration, we know that it's not first order. So 0 first, second. No, it's not first order. For zero order reactions, as time goes on, the half-life is going to get shorter and shorter and shorter, which means it takes less and less time to cut it in half, which means that the rate, I guess also for zero order, the half-lives decrease, the rate stays the same. For second order, the half-lives get longer, the rate's going to decrease over time. So plot of the natural log of the concentration of the reactant as a function of time is linear. Can't be that one because that's a first order. The half-life of the reaction increases as the initial concentration increases. That would be zero order. And then C, so we know it's not zero order. So it has to be second order. So we have to really pick which of these is second order, and doubling the initial concentration results in a quadrupling. So 2x initial concentration, 4x rate, second order. Oh good, they fixed that clock. Right on. The next thing that I just want to introduce is now we're going to talk about the Arrhenius equation and the effect of temperature. So we've got these rate constants, but those rate constants are only good at a single temperature. It only works for that one temperature. The rate of the reaction, that constant K, actually depends on the temperature of the solution. And for almost every reaction, increasing the temperature increases the rate. And it increases the rate because we're increasing the amount of energy present. As a rule of thumb, a 10 degree C increase in temperature can double or triple the rate of a typical reaction. This is part of why body temperature has to be maintained so precisely, because if it increases or decreased wildly, then you get massive increases or decreases in rates. So it's only at a single temperature. So you have the Arrhenius equation, which looks like a lot, but we're going to break it up into the different parts. You have this frequency factor. This is all to define K. So K depends on this frequency factor, and it depends on the exponential factor. And inside of this exponential factor, we have the activation energy, which is the EA, and we have temperature. And then R is just the gas constant, which this is the same as the gas constant that you use in PV equals nRT. It's just different units. So you get the different units, then it's joules per mole Kelvin is 8.314. And the temperature has to be in Kelvin. Yeah, I guess that's a little farther in. Now we'll go to the next slide. So even though we might have a reaction here, if you remember reaction energy diagrams, we've got a higher energy of the reactants, lower energy of the products. That's energetically favorable, which means that if we can get over that hill in the middle, that activation energy, then our products are most likely going to stay products. And we'll get energy out of this reaction. So you get extra energy released, probably just as heat. So that energy of activation is that energy barrier that must be overcome. The frequency factor A is the number of times that the reactants approach the barrier per unit time. So how often are my atoms and molecules even getting close to that energy barrier? Because if you don't have the energy to start it, I mean, this is the same reason that like gasoline doesn't just spontaneously combust, or other things like wood and stuff doesn't just spontaneously combust. There's not enough activation energy, or there's not enough energy in the system for it to start the reaction and catch on fire. But if you have oily rags, you never clump those up and then put them in a trash can, because the oxidation process reacting with the air will generate heat. And if it's a bunch of rags that are all bundled up, it'll insulate that heat. And it'll get warmer and warmer and warmer until there is enough energy that it will start a combustion reaction and spontaneously combust. So if you look at, I wanted to look at this is just a reaction of something interconverting. So you got methyl isonitrile and acetonitrile, and one is more stable than the other, the acetonitrile is. So it really does energetically want to be acetonitrile. These molecules, or the nitrogen and the carbon, can flip to change places to become that more stable form. But in order to flip, you have to almost break this bond between the carbon and the nitrogen. And that takes a lot of energy, because you have to go through this really unfavorable state where you've basically almost broken the bond and it will snap into the other position. And that can happen just because as you add heat, things are vibrating and shaking, and so it might torque and twist. And if it torques and twists enough, then it can flip. But we have to be able to get over that energy barrier. So we got our activation energy, which is the energy to get up the hill. And then we also talk about the energy of the reaction, or the enthalpy of the reaction, which is the difference in the energy of the reactants and the products. So as these bonds go to this awkward, painful transition state, takes a lot of energy, but once they flip over, they release extra energy. So if I increase this activation energy, I make it harder to get over that hill, you decrease the rate of reaction because there are fewer molecules that ever get up the hill. which is making it harder to get over. And so you get a slower rate. And we can even look at, I think we're going to talk about K. Oh no, frequency factor. The frequency factor is how often you even end up with the sort of series of contortions that would start to go up this energy hill. Because it might not even be moving in the correct direction. Or when you talk about reactions between two different atoms or two different molecules, it's how often they collide in the correct orientation. So you might see a reaction like hydrogen reacting with iodine to make, these are the hydrogen, like H2, this is I2, and then you get 2HI. They have to collide in the right orientation in order for that reaction to happen. And probably a side to side, like I've drawn them there, where the bond between the hydrogens can break and the bonds between the iodines can break, and they can form these new molecules. If they don't collide in that orientation, they can't react. And that's part of the frequency factor also. When we're talking about a single atom, it's sort of how often does it start to rotate in the right direction, and then does it rotate with enough energy to get over the hill? So your frequency factor might only be like 0.1 or less. It could be really small. And then our exponential factor is the amount of energy, or really it's the distribution of molecules that have enough energy to get over the barrier. So we're multiplying one fraction by another fraction. If the activation energy is 1, that means 100% of the molecules have enough energy. And then we multiply that by our frequency factor. So here, if our frequency factor is 10 to the 9 per second, and our exponential is 10 to the negative 7, then we only end up with 10 to the second per second. Basically multiplying two fractions by each other. And this exponential factor is actually in the form of or actually represents a distribution of energies. And you have to think about 1. So if this is 1, 1 is 100% of the time it reacts. 0 equals 0% of the time it reacts. So if my activation energy increases, does my exponential factor get closer or farther from 1? And it might be easier to actually just, if we drop most of this and think about just, like if this was e to the negative 2, I don't think you can see that. Yeah. So if I do e to the negative 2, that's 0.135. E to the negative 3. So right, if the activation energy increases, I would get a larger number there for my exponent. E to the negative 3, so that's 0.0497. So as the exponent in the exponential factor becomes a larger negative number, our frequency factor is actually decreasing, or actually our exponential factor is decreasing and becoming a smaller number and getting closer to 0, where none of our collisions are at enough energy. So we know increasing temperature increases the rate of reaction. How does increasing temperature get me closer to 1? in the exponential factor.
Will be the smaller, the smaller the answer, right? So the closer it is to 0, it's going to go to
Yeah, yeah, yeah. So if we just zoom in on this, if this gets larger, I'm dividing by a larger number, which makes that whole exponent smaller. And then we know anything raised to the 0 would be 1. So as we get closer to 0 in that exponent, we get closer to a factor of 1. So increasing temperature, it's in the denominator here because this whole thing needs to get smaller for my reaction rate to increase. And you probably just need to like write this out a couple times. Plug some numbers in and plug it into your calculator and see how the math changes, because there's a lot of negatives and there's a lot of weird things that happen here in the equation that can be counterintuitive at first. But when you really examine where those numbers are going into and how they change the equation, then you can better understand how that matches up with the real world. All right, and we'll talk about the rest of the effect of temperature later on Wednesday.